Let's talk about computation-communication overlap. When talking about GPUs, much of the focus is on the throughput of these models, how to get enough flops in order to train large language models. But to use these flops requires much of the actual parallelism itself, and that requires passing things around. We have to pass activations between different layers. We have to pass gradient states in order to do updates. This requires a lot of network communication, both locally on device and over our cluster. One thing that's interesting is that GPUs provide basically a parallel mechanism for doing this communication, and that doesn't actually stop it from doing the computation itself. So if you can set things up so that the communication and the computation overlap, you can get the best of all worlds. But this can be pretty complicated. When reading large language model papers, you'll often see diagrams that describe the various overlap between communication and computation. These diagrams will often be just two rows, where the top row shows the order of the serial computations that have to be done, and the bottom row shows the communication that's actually happening. Basically, in order to compute various things, you'll have to do them first in order for the communication to happen at the next step. If these don't line up, you'll get bubbles, such as the ones shown here, where you're not actually able to do the model update until you get the communication from the reduced scatter on the step below. This can be quite bad, as it means you're not actually running your tensor cores during this step, as you have to wait for some communication to happen. In the recent DeepSeek v3 paper, they have quite a complex diagram where they describe the computation and communication of their system. In specific here, they are actually running two different batches in parallel, one going forward and one going backward. The key idea is not how they do this, but how this allows them in order to do communication at the same time they're doing the computation of the system itself. In complicated modern systems that often have many forms of parallelism, in this example here, both pipeline parallelism, expert parallelism, and data parallelism, you have actually a huge amount of computation time at the bottom of the slide. But in order to basically put that in the right place, you have to figure out how to line it up with the computation that's actually bottlenecking your system.